Welcome everybody to my talk on C++ for embedded systems. My name is Steve Bush. A little bit of background on today's talk. I'm going to be going through kind of a pretty breezy set of topics on embedded firmware and the C++ language. So we're going to be working on breadth rather than depth. So we're going to cover a lot of things. Hopefully you will enjoy them and take some tidbits back to your job or hobby. And so, like I say, it's going to be a bit more breadth than depth. In keeping with Bjarna's talk earlier this week on C++ and constrained systems, for embedded developers, it's maybe less about delving into the deep, dark recesses of the language, more than picking out the really good parts that make us productive and without a lot of cost. So let's go ahead and get started. So a little bit about me. I'm Steve Bush. I'm a research fellow at the Procter & Gamble Company. Maybe you've never heard of our company so much, but P&G is a global manufacturer of consumer goods. We make a lot of brands that you may have in your home in terms of cleaning and household care products. So I'm an embedded product developer. I work in a upstream R&D division of P&G, where we work on connected and smart products. So I do hardware development and a little bit of everything, mechanical too. But one of the things I really am passionate about is C++ and making firmware development a bit more of an art form, at least as much as possible in our constrained systems. So at P&G, we have a number of brands that you may be familiar with, probably some that you have in your home. So we have a lot of cleaning products and baby care and oral care and grooming and so forth. So you probably see brands here that you recognize. We are a consumer products, like a consumable products company, but at the same time, we do have a significant business in devices. So think our grooming businesses with shavers, oral care with its toothbrushes, and household care with some of their freshening and cleaning durable products. As I said, I work in the upstream division where we look at smart and connected devices. These are some of the devices that are near and dear to my heart. We've shown them at the CES show, formerly the Consumer Electronics Show. The upper right is the Area product, which is a smart and connected air freshener that doesn't just do one room in your home, but your whole house. Opte in the lower left is a makeup dispenser that uses a smart system integrated with the camera to basically do Photoshop makeup on your face, right? So Photoshop for your face. One that's really near dear to my heart is the Oral-B toothbrush. That's the IO10 that's getting ready to come out. It's a really fabulous product. It has onboard artificial intelligence or machine learning algorithm that interprets movements of the brush as position in your teeth, gives you feedback on how you're doing in brushing. So, like I say, I'm really proud of that. We got lots of pretty cool code running in that product, and I'm going to use that as example, kind of inspiration for the examples that I'll be talking about later in the talk. So today's objective is really about making embedded code easier and more pleasant to write and maintain. The things that we'll be talking about are not super sophisticated, but hopefully they are things that you can take home and make your code easier to write and read and understand, and therefore make them objects of envy for your embedded friends that use the C language. So the agenda, we're going to cover, like I say, kind of a lot of topics. GPIO configuration, compile time, lookup tables, an interesting way to look at numeric constructs, data structures, stream-based I/O, heap memory management, and when it's appropriate, and some library features like stud chrono and stud random. I got a lot to cover, so honestly, I'm not going to take questions along the way, but we'll see if we have a little bit of time at the end. And my commitment to you is that I'll be on the Discord for those that are watching this live. I'll be on the Discord to answer questions to make sure you get your questions answered. So at the end of the week, there'll be a companion repository up at my personal GitHub, so sgbush. So you can kind of refer back to the slides and come back to this link. By the end of the week, I'll have some example code set up. It'll be very short snippets, no grand examples or anything, just very short snippets that hopefully get the point across. Let's dive right into it. First is configuring GPIO declaratively. So GPIO, or the I/O pins on our embedded product or microcontroller, typically that's sort of the base thing that we need to do first in configuring our system. And this is kind of the old way, the way we see it in example code or code generators, where you have a init structure, and then you start filling it in with things like what's the pin number, what's the mode of the pin, is it push-pull or open drain, electrical modes, speed, and does it have an alternate function? So for an alternate function, maybe the pin is connected to another peripheral in the chip, like the UART or a serial bus. So what we do is, having filled in the blanks on that, we sort of procedurally configure that I/O point, and oh, by the way, don't forget to do a write, so that you write the correct logic level to that pin. So you don't want to accidentally turn on a motor or indicator light when you don't mean to during configuration time. And remember that a lot of these are plain old constants, so they're not strongly typed, and so there's a potential for error there, and the syntax highlighting doesn't help you out much, right? And since this is procedural and we have a lot of I/O, then we pretty much go through the same procedure again, kind of rinse and repeat, set some more fields, do configure, do write, and so forth. So here's a better way of doing it, at least the way we do it in some of our code bases. So we create what I call a GPIO def structure, which is again a structure, and this encapsulates everything we know about our GPIO peripheral. So the first is the actual hardware port itself, and then the pin number on that port. And then we have a bunch of enums that describe the function that we want out of that pin, whether it's input or output, maybe an alternate function that's connected to another area in the chip. And then other parameters that say what's the speed. And then finally, at the end, what is the initial state that we want that I/O pin to end up in. So what we can do is use a std array, and of course this can be declared statically with no dynamic allocation, right? So all we do is have a std array of GPIO defs, however many GPIO defs we want, and then we sort of declaratively show what we want our GPIO pins to be, right? So we have our port B, pin 0, we describe its input-output function and so forth. And we use enums to give us a little more typing control, a little more strictness in typing, and then we can do multiple of these all in one go. So basically, we declare all of our I/O and its functions all in one spot. So just a word about this approach. We use weak enums, and that's just a design choice. That's not required. You can choose to go another way. We use weak enums because they convert implicitly to their underlying type. So if you're smart about setting what the enums values are, numeric values, then they can be helpful in setting the registers when you're configuring the I/O. But they're constrained to tight scope within that GPIO def structure. So using them in an inappropriate setting is maybe a little more difficult to do. We find that the syntax is pretty expressive and easy to maintain, and it's pretty easy to consolidate the entire project's I/O configuration all in one place. And indeed, that's the approach that we want to take that I'll describe later. So configuring and using I/O definitions, as I said, we prefer to kind of configure all in one go. We have our I/Os declared declaratively, right? And so we want to do that all in one go. And not preferred is we want to pass around those I/O defs to delegates and have the delegates figure out what they need to do with the I/O. So a bit more detail on that coming up. So in doing this approach, we have to write one function that is a bit tedious to write, right? So this is a configure function that takes a GPIO def as an argument. And in this function, you would sit down with your 2,000-page reference manual and go through the registers and kind of convert all those enums and so forth to register settings. So this is a bit tedious to write, but the good news is that you only really have to write this function once, and it's probably good for the entire family of microcontrollers that you're hoping to use. Having written this function, then you can write another function, which is much easier to write. So this is just a configure function that takes a set of iterators, begin and end. So this is sort of the classic STL iterators way. And so you just iterate through that std array, that iterable container, and configure the IO pins one by one. So kind of working away a little more to the modern end, we can also write a configure function that is the std ranges way, right? So we have a template, and we use my news best friend, which is a requires clause that requires the type that we pass to this function to be a std range. And of course, a std array as a iterable container qualifies. So we just iterate through those IO definitions, configuring each one by one. So this is really simple. I mean, literally, this is all you would need to write in a minimal case. So I mentioned, what do we do about passing GPIO references around? So as an example, I'm going to use this SPI bus. SPI is Serial Peripheral Interface. It's a serial bus that's frequently used in embedded systems. And the model we're going to use is that we're going to have a struct for the hardware bus, right? So this represents the bus peripheral in the chip. And then in addition to the hardware, we have a protocol. So the SPI has a mode that describes its clock polarity and data polarity and so forth, as well as a transmit speed. And then we combine those into an SPI connection. So our SPI connection has a hardware bus, a protocol, and then the thing about SPI is it's a bus with multiple slaves or chips attached to it. And the way we communicate to those slaves is we assert a chip select. And the thing is, we could just pass this GPIO def along to the delegates, to the downstream code. And the downstream code, we have to know that in order to select a chip, we actually have to set the pin as a logic low. So in this case, we might think that that is a little bit too much responsibility for a downstream code. So maybe we'll take a different approach on how we want to pass down a chip select. The approach we're going to take is we're going to write just a tiny hierarchy of classes. First is an assert type, and then an assert type logic high, which just has a value inside it that says true. That is, when asserted, the logic level is high. And then the opposite type, when asserted, the logic level is low. So the important thing is it just has these two little booleans. And then what we can do is write a functor. A functor, for those of you who don't know, is basically it's just a class. It has a little piece of data in it, and the data that we have that we pass into it is a GPIO def, that representation of an IO pin. And this class can be called as if it was a function. And we call it with just a Boolean enable. So if we enable or assert this IO pin, this value when asserted is then used to determine kind of the correct action to take. And here we're just setting the registers in order to set the IO pin to the correct logic level. How might we use this? What would this look like? So again, we come back to our SPI connection structure. We have as a member this GPIO assert functor as an enable function. And that gets passed to the SPI connection when we construct it. And then our SPI connection has a read-write function, right? So as you might think, it has some output data and an input data, and what's the length of the data that we want to transmit. So in doing this, we simply call the enable function with the true, meaning we want to assert it. And the type that we passed in determines what happens when we assert that pin, which means that it's actually asserted as logic low. Once the writing and reading is finished, then we deassert the pin, and the write logic level happens, right? So let's kind of bring it all together and see what it looks like. So we have a std array of our GPIO defs, our IO pins, and again, this could be the IO definitions for our entire project. We configure IO pins all in one go, just with one call. Then we construct our hardware bus, and then our protocol that runs on our hardware bus. And then we define as our chip select this GPIO assert function with assert type logic low. That means when we want the chip's attention, we're going to assert a logic low and pass to it the appropriate IO pin. So finally, we create our SPI connection. We pass our bus and our protocol and our chip select function. And this way, we take responsibility for everything, including the design decisions around whether that what does asserting a chip select mean. So wrapping this topic up, centralize your IO definitions and do them declaratively, and you can abstract IO functions. And actually this functory approach that I showed you really comes with little or no cost compared to some of the other options that you might have. Next topic, creating lookup tables using compile time expressions. So lookup tables are a really common feature of embedded systems. So I'm showing an example here where we have an array, temperature from thermistor. A thermistor is just a nonlinear voltage device or resistance device that relates resistance to temperature. And so this is a really common application where we might have an array of temperatures. These are just floats. And each one of those temperatures corresponds to an ADC or analog to digital conversion value. So for each ADC value, 0, 1, 2, and so forth, we have a temperature conversion, a temperature value that corresponds to that code. So frequently we would generate this data via spreadsheet and then copy and paste it, or we might do it via script and copy and paste, or if we were pretty sophisticated, we may generate a header file via script and incorporate it into our build system. But all of these options kind of have some complexity and potential for error in them. So some considerations when we're talking about lookup tables. In embedded systems, constants or these lookup tables really have to be carefully crafted so they end up in the RO data section. What this really means is that our lookup table is going to be placed in flash and not copied to RAM. So in an embedded system, flash is a limited resource, but it's a lot less precious than RAM. Usually the RAM is a really precious resource. In our embedded system, we want to make sure that our tables don't end up in RAM somehow. The consideration on the hardware is it's very common for hardware and firmware to evolve together. So the example I have here is a resistor divider. It has a plain resistor and our thermistor temperature sensor that yields a voltage out, right? So in the course of debugging our hardware, we might decide that this upper resistor here needs to be changed out to a more appropriate value. And we might do that, for example, to move the temperature readings into a more linear range of the thermistor. So in doing this, we'd really like to incorporate our governing equations into the code and let the compiler generate our lookup tables, right? So these are the things that we might need, right? So the first is the analog conversion, right? So we have an ADC code, analog to digital code, that's converted to a voltage using this expression. And then we take that voltage and convert it into a resistance using this expression. And then finally, we take that resistance and then turn it into a temperature using the Steinhart model, which is really kind of like a Taylor series expansion. And you can see that this is a pretty expensive function, especially on an embedded system. So this is definitely something we would want to kind of condense into a lookup table. And what we can do is we can use const expr expressions to both do the calculation to compile time and document our code right in the source code. So going parallel to the previous slide, we have a const expr function, voltage from code, and we just pass some parameters, including the ADC code, and we yield a voltage out. Similarly, we have another expression, resistance from divider, where we take that voltage and then turn it into a resistance. And we have finally this kind of Taylor series expansion, thermistor value. So we pass this function an array of coefficients. And the nice thing about doing this is templated on an integer value, which is just the length of this coefficients. So for a thermistor, we might look in the data sheet and find that they give us 2 or 3 or 4 coefficients, and we can plan appropriately because we just simply iterate over the coefficients and use powers and logs and so forth to calculate the temperature. So, and to reiterate, this is a const expr function. Everything here is known at compile time, so the compiler can do all of this figuring for us. We have our thermistor table generation function. So we pass our array of coefficients and a bunch of other parameters that are known in compile time. We create a standard array of floats. The floats are going to be temperature, and we're going to create 256 values, one for each possible analog to digital conversion value. So again, we just iterate over every possible ADC value, calculating voltage from code, resistance from divider, and so forth. How might we instantiate this? What does this look like in our actual code? So we have our coefficients here, thermistor coefficients that we can take from the data sheet. In this case, there are 4 of them. We use our function thermistor table to create our thermistor lookup table. And again, this is done at compile time. And then later in our application, that thermistor lookup table is available for us to do lookups, or in other cases, state space relationships if we're trying to shortcut our control algorithm, and so forth. So what I emphasized earlier is we want our table, lookup tables to end up in the constants or flash area of our chip. And so that you don't have to take my word for it, let's take the example that I showed and cross-compile it and look at the binary. So if we look at the sections, we go down and look at the RO data section. We know for a fact the RO data section is going to end up in flash, and we need to take note that that's section 18. And then we can look at our symbol table, also an ELF file. So do a read ELF and look at our symbols. And we scroll down and we find our lookup table, thermistor lookup. And we find indeed it is in section 18. So this is definitely going to go in flash as a constant lookup table. We also noticed that we had 256 values in our lookup table. They're floats, so it's at 1024 bytes. This is in fact the correct length. To sum up, lookup tables can be very fast and time saving or space saving. And these are really often critical for embedded real-time applications. The nice thing is we can place the design support in the source code. There's no external processes like a build process that or a copy and paste that can lead to mistakes. Lowers the complexity in the build process, right? So when we make a change in the hardware, we can just change it into source code. It gets pushed up to the to our version control system. So that it's documented, and of course tables reside in non-volatile memory. So next topic, code with numeric structures that humans can actually read and edit. And this is a topic that's really near and dear to my heart for reasons that I'll talk about here in just a moment. So just like the previous example, a lot of embedded applications use long numeric structures, and they're frequently known at compile time, and we would prefer to store them in non-volatile memory. Some examples are Bluetooth. If we have Bluetooth services, we might have 128-bit UUIDs or a MAC address that's static. Same thing with the IP. If your device is Ethernet connected, we might have IPv4 or IPv6 addresses that are static. Similar thing with USB. Obviously, these are not like strictly numeric structures, but USB is a little unusual in that it takes Unicode encoded string descriptors. And so all these are a bit difficult to deal with in sort of the ordinary C world, but we can use features of the language in C++ to really make these easier to deal with. And I'll show you how we do that in our code. So address like structures the old way, right? So this is the canonical UUID. So this is the way we would see it in our documentation, with braces and nicely segment it out. But if we were just to kind of do it the standard way, with an array of bytes, we would have it just as an array like this, which I find kind of pretty difficult to read and understand and change. So the same thing is with the canonical MAC address, right? So we prefer to look at it in the canonical way, but we tend to store it as an array of bytes like this. Same thing with IP4 addresses. We might have an address and a mask bit structure, and sometimes that's a little bit hard to read and understand. I think it's especially the case with IPv6 addresses. So IP6 addresses obviously are very long, but the convention is that we have shortcuts to describe those addresses in a really short way. So like we've shown here, but if we kind of take the classical approach to numeric data, as an array, then we have to explicitly call out all the parts of the address, like including all the zeros that we would typically kind of overlook. Similar with USB strings. USB string descriptors have to be encoded as Unicode. So I don't know about you, but I've seen this lots and lots in generated code or example code where like a device descriptor or other string descriptor in USB is written like this, with interspersed with zeros, so it is Unicode. But again, you have to remember, oh yeah, we're in a little endian system, so the zeros have to go in the right place and so forth. Or if you take a bit more data structure approach to your string, you can have, well, what is the length of the string, and then what is the standards-based ID of the string, and then we have the Unicode data. Or worse yet, we can have a C-type macro, which converts our string letter by letter by letter to this Unicode format. And I don't know about you, but I find this like really, really difficult and frustrating to work with. And so there's really got to be a better way. So this is the approach that we take. So we can imagine a UUID class, and we're just going to take the simplest possible approach to the data storage part, right? So it has a private data storage of a std array that just stores the data in bytes. And it's pretty ordinary, other than it has this operator quotes, which is the user-defined literal operator. And we just define this as both a friend of this class, so that it has access to its private data structure, and also const expr, so we can construct UUID objects at compile time. So let's look at this, this user-defined literal operator in a little more detail. So what we're doing here is we declare, again, const expr, so evaluatable at compile time, operator quotes, and with the underscore UUID, and again, this is the user-defined literal operator. And we're going to be passed within the quotes, what is the text in the quotes and what is its length. And so what we're doing here is we're just doing a very simple as possible hexadecimal parser, right? So we're just taking the characters 0 to 9 and translating them into the corresponding data. Same thing with hexadecimal A to F, and then capital A to capital F. And then as we're parsing through, we can check for bogus characters here. If there's characters that we don't want to be in our string literal, we can reject them here, or we can do as we're doing here, which is we sort of implicitly pass over them with doing nothing. And the nice thing about being a const expr expression, when we do this as a string literal, we're allowed to throw exceptions. And so if we have something that doesn't quite add up in our string literal, our UUID literal, for example, that doesn't have 32 valid characters, then we can throw an exception that has a meaningful error message. And again, this is going to be thrown at compile time where we can catch it. How would this work in real life? So using the sort of the simple structures that I showed you earlier, we could declare our UUID as such, and we just pass the canonical version in the form of this user-defined literal. Same thing with a MAC or an IP address and so forth, right? All of these can be then parsed into structures that are useful for us in our application, including this USB string literal. So this can be parsed into as much sophistication as we want, including the length, the USB standards codes and so forth. One thing I want to point out is the C++ standard does give us kind of a Unicode literal, which we could use. One thing to watch out for, though, is this Unicode literal will give us a Unicode null terminated literal, which in fact is going to be one more character than we actually need for a USB string descriptor. Remember, USB, the string descriptors are passed along with its length, so it's not null terminated. So this is a really nice feature that we use for our statically declared data. It just makes looking at our code, understanding it, and changing it really a lot more pleasant. So next topic, using stream-based I/O, but skipping the library. So everybody kind of recognizes this. This is a simple Hello World application. The way we've gone about it, though, is we've used I/O streams. And we're just doing, we included I/O stream, and we're simply doing Hello World to standard out. So what we can do is we can go and cross-compile this, and I've included all the details here, the gory details about cross-compiling it, just to be transparent of what I've done. We've optimized for size, and we've thrown in a few things that will sort of trim down the code size in the typical case so that we get a reasonable size binary. And then we convert this into our binary so we can see, okay, how much space is this going to take up in our embedded system. So what we can do is we can compare a bare main, it is literally a main application that is empty, with what we just compiled up here. So the 1.7K is basically just kind of the interrupt vector table and a few other things, but simply adding I/O streams and saying hello world has added like a lot of code to our application, and really all of this stuff is going to have to be stored in Flash. So kind of the point here is there a way to do this but kind of avoid a lot of the overhead that we incur in using this sort of the typical I/O streams? And the approach that we're going to take is we're going to create a lightweight file stream object. So we're going to create a namespace, MCU, create this class file stream. And within this, we're going to define a type. So we're going to ask that our file stream object be able to output a stream of formatted integers, right? And we like to be able to specify that those integers be presented to us in whatever radix we want, right? Decimal, hexadecimal, binary, and so forth. And this will be super useful for us for debugging purposes. As far as data, this file stream object just has a couple little pieces of data. It has a Unix style file descriptor, which is nothing more than just a number. And it has this radix setting, so our file stream can remember what radix we want our output format to be in. And so we have just a very simple constructor like this that just takes the simple file descriptor, the numeric file descriptor. And then we get to kind of the meat and potatoes of our file stream class, right? So this is the stream insert operator, and this is the overload that takes string pointers. And what we do here is just take the length of that string, and then we delegate the writing to our syscall or write function. And I'm going to talk a little bit more about this write function later. We just pass the file descriptor that's part of this data structure, as well as the string and the length. We can go and do this for other data types as well, right? So here we've constructed a stream insert operator for integer type data. And again, I've templated this and then use a requires clause. And again, this is kind of my new best friend because we can craft this overload to take a number of different data types, and it's very descriptive about the data types that we're going to accept in here. So really super new feature of the C++20 standards release. So again, the job of this function will be to turn our integer into a string representation and then pass it to this write function. And same thing with floating or whatever other data type that we would want to be able to have in our output stream. So how might we instantiate this? It's pretty simple. Again, in our MCU namespace, we decide maybe we're going to have two output streams. One is going to be our debug output, and perhaps this is connected to our UART output that's connected to our board. And then maybe we have another debug output, SWO, which stands for serial wire output. Serial wire output is really just a facility of the debug probe. So in the event that we don't have like a UART or another output means attached to our board, we can get the debug output out from the debug probe that's attached to it. So two different options here for getting output out from our embedded system. So I mentioned this write function. Really, the underscore write function is a syscall, and it's basically the plumbing for our various output modes, right? So our underscore write syscall takes a numeric file descriptor. It takes a data, which is basically a string, and it takes a length of that data. And then we further delegate it to our various hardware functions, right? So one of them might be our SWO, serial wire output write. So this passes through our debug probe. In another file descriptor case, we pass through our UART function, and we can extend this to whatever debug functionality we want, right? So if we're Ethernet connected, we might have a UDP write that then goes out to a UDP listener out there that we are using to debug our system. So how might this look as we use it in our application? So instead of IO streams, we include our new file stream utility. And in our main, instead of hello world, using the standard output stream, we use our MCU SWO to say hello serial wire debug, or use our MCU debug stream for a UART debug. So so we can have various output streams, use them for different purposes and different phases of our debug use case. The nice thing about this approach is it's actually pretty small. So if we include all the hardware interface functions that you would need to make this work, and I have an example that shows this, and we go ahead and compile it and then convert it to binary. Here is our trivially empty main function in our 1.7K, and a fully functional example, that we show above here, along with writing to the hardware. What we're calling main better is 2.3K, so just about a half a K or so additional code, which is a whole lot better than our typical IO streams at 157K. So we're able to get kind of lean, mean stream-based IO for really not much cost. And we can add some bells and whistles to our stream function, right? So here we have a troublesome function that we want to debug, right? So we might have some numeric values or string values that we want to dump. So what we can do is use our MCU debug output stream and specify, hey, the next value that we want to have come through is we want it to present it as hexadecimal. And so we pass our numeric value in, and then we get a nicely formatted hex value. So it's pretty nice, and this is easily extensible. Though you may be asking, okay, what's wrong with printf and kind of the usual output formats and so forth, and why would we use this instead of say the new std print that's coming in the new standard? We find that it's really useful to extend to other types, right? So earlier I mentioned that one of our really common applications is machine learning inference, right on the edge. And of course that is, part and parcel of that is creating tensors and operating on tensors and doing those functions. So we frequently have an opportunity, we create tensors and we need to look at them in the debug stream. So what we would do is simply create a new stream insert operator for our file stream class, pass it a tensor, and then we would iterate over each of the dimensions in the tensor. And at the base of that tensor is just simply elements, and we would pass those into our stream functions. And so here we have a pretty simple way of expanding our I/O functions to include how do we output tensors. And let me show you how that works. So here we're declaring a tensor result. It's going to be a 10 by 10 tensor, and just say that we want to see that in the output stream. So using the method I had in the previous slide, we could simply output something to the debug stream that looks like this. So pretty easily extensible to all sorts of data types, USB types or any sort of complexity of data types that you want, really just by writing a pretty easy to write function. And so this is really for us the magic of using stream-based I/O. It makes debugging so much easier, and it's really extensible to all sorts of types. For the next topic, I'm going to grab the third rail of embedded systems with both hands, and I'm going to say that we can dare to use the heap. Of course, that's going to come with some caveats, and you probably only want to do this in non-safety related applications. But using heap in embedded applications or dynamic allocation is usually a no-no. Runtime behavior can cause heap exhaustion, right? So we might not plan for the corner cases where we would want to try to allocate more memory than we have available. Sometimes long runtimes can cause fragmentation of the heap. And that's really problematic because we have enough memory, we just don't have a contiguous piece of memory that's suitable to allocate. And typically heap errors have no graceful resolution, right? You typically end up in some sort of crash, and that's really no good, especially for safety-related applications. So as a result, many applications stick to static allocation, right? So that means that a lot of our dynamically allocated containers are off limits, right? Stood vector, stood map, list, double-ended queue, and all those really nice things to use. But I'm going to propose that we can imagine an allocate once scenario where heap is actually reasonable and desirable to use. So the example I'm going to use is goes back again to this machine learning inference that we use in some of our products. As part of that, we construct a calculation graph that is a sort of a directed graph of calculation nodes, right? So we have a class calculation node, and this node we define a sort of a shortcut handle to pointers to other calculation nodes. And really what this is sort of a fancy linked list, sort of a calculation node with child nodes. So we have a iterable connector collection of child nodes. And this calculation node can do one of two things, right? We can override this calculate function so that it kind of does useful work for the calculation. Or if this calculation node has child nodes, it can iterate through those child nodes and ask those nodes to calculate them. So in this way, we build up a directed graph of calculation that's sort of the bread and butter of our machine learning inference. And since we're doing machine learning and we would like to update our machine learning models, maybe even the topology of that model, we would really like to be able to kind of dynamically allocate this structure of nodes. But the thing is, it's only done at initialization time. So once we configure and allocate everything, that's it. There's really no deallocation. And this is deterministic in the sense that we know the data that we're passing to our application, so we know that we're not going to overrun the amount of memory that we have available. So this case is a good opportunity to maybe use arena allocators. So arena allocator is useful for kind of monotonic allocate once applications. That is, you only allocate memory, but you never deallocate memory. It's really fast, it has very low overhead, or really no overhead, because we're simply dispensing with all the bookkeeping that's required for allocation and deallocation and reallocation and so forth. So preferably we have deterministic memory usage, which we said we do because our data is known to live within the memory constraints we have. Arena allocators, I'm going to talk a little bit about them, but only on a very superficial level. So I recommend you kind of take a look at John Lakos's talk or Bob Stiegel's talk, where they go into arena allocators in a lot more depth than I'm going to. So kind of the most basic, most simplistic way of using arena allocators is overriding the global new operator. So what we do is define our own new operator. And what we're going to say is it's going to have an arena size. And then we're going to statically allocate an arena, a memory chunk of that size. What we can do is calculate a pointer within that arena that's offset by the number of allocated bytes. Then we advance our allocated bytes count by the size that we're trying to allocate. And we return that pointer. So basically all this is doing is taking that big chunk of memory and sequentially doling out chunks of that in a very, very sequential fashion. Now, overriding the global new operator is not for the faint of heart, right? We have to really make sure that other parts of our application doesn't rely on having allocation and deallocation, and there's some other pitfalls that may happen here. So another option is to override new on a per class basis. So in order to do this, we're going to define a class called arena allocator. And just like our other function, it has an arena size and it has a statically allocated arena of that size. And it just has an allocate function, which does exactly the same thing we did before. It just doles out chunks of that arena for use by our code. So we can rewrite our calculation node in a different way here. So in calculation node, we're going to override the new operator for that class. And it's basically the same. We just have an instance of that arena allocator and ask it to allocate ourselves a chunk of memory. And what's going to happen here is every time we new up a calculation node, it's going to use this new operator to dole out dynamic memory. And the thing we have to watch out for is within our calculation node class, we do have a dynamically allocated container, this std vector. So what we can do is pass this std vector our arena allocator type so that we can ensure that as we add elements to our std vector container, that is, we add child elements, that that container is going to use our allocator to allocate memory as well. So in this way, our whole calculation tree can function to use this arena allocation stream, but not necessarily mess with the allocation system that's going on elsewhere in the application. So let's try a death-defying demo here. So let me walk you through just a little bit of code that we're going to use as a demo. Here we have an operator new. And this is doing basically the same thing as I showed you on the other slide, other than I have a little constexpr switch here that says either we're going to use this arena allocation method or we're going to use the sort of traditional malloc method. So I have use arena as false. We're going to set it to false first, if I can type. Then we're going to go over here, and then we're actually going to build and run this on a development board that is attached to my computer, my desktop right now. So we're compiling, we're actually flashing onto the board, and we find the number of allocations is 341. And let me show you what we just did here. So our main function here, this is the heart of what we just did. We just have a loop that allocates pointers of size t until we're exhausted. So we've just allocated until we can't allocate anymore, and then we've used our MCU debug facility to display our number of allocations. And we see our number of allocations is 341. So what we can do is go back and now use our arena allocator just by setting the switch. And we'll go back and build and run again. And again, we'll compile and flash to our development board. Now we find that the number of allocations is a lot more, right? which you would expect because using arena allocators, we've just kind of done away with all the bookkeeping, right? So as a result, we're able to do 3 times the allocations in this trivial little example as we were able to do before. So, all right. And to kind of wind this topic up, it's possible to do allocation while avoiding pitfalls of fragmentation. It's important to do that at initialization time and be thoughtful about what we're doing, but we can avoid heap overhead and really do some pretty interesting stuff. So, but the moral of the story is be safe. All right. So the next function or next section comes with a really grand title of implement one function to unlock all of time functions. So we're going to show a little feature of the some code that you can write to unlock some features of the C++ standard library, specifically std Chrono. So if you ever look through std Chrono, the CPP reference in your free time, and of course who here doesn't, you'd find there's some really interesting stuff in std Chrono. Some really nice timing and calendaring functions. And in terms of embedded systems, there are kind of 2 different flavors. We have a relative time, which might be a hardware timer, where the hardware timer counts from 0 to some very high number and then wraps around again to 0 again. And then we have absolute time, which might be our real-time clock. So the applications is maybe relevant for our performance instrumentation and maybe time and day and calendaring. So in our quick little example here, we're going to kind of concentrate on performance instrumentation. And what we're going to do is show you how to unlock std Chrono. So the first thing we're going to do is write a little function that configures the hardware. What we're doing here is have a microsecond clock configure. And what it's going to do is configure a hardware timer to be a monotonic timer counting microseconds. So what we do is pass the hardware representation of our timer and a few configuration parameters, and we're going to ask for a timer frequency of 1 megahertz, which corresponds to our 1 microsecond tick. What we're going to do is just set our hardware registers, turn on the timer, set some prescalers and so forth. And so this timer is going to count from 0 up to hexadecimal all Fs and then wrap around and go again. And so we've configured our hardware microsecond timer. What we do is in the std Chrono namespace, we're going to overlay our own version of this high resolution clock now function, which is just a simple function that returns a std Chrono time point. So the now function just returns this time point. And all we do here is we have our microsecond counter. Again, this is just a value in microseconds, and we convert that to nanoseconds. So we take microseconds, multiply by 1,000, we get nanoseconds, and then we return that as a time point. All right, and let me show you what we can do with that simple little bit of code. So here I've got just a simple benchmarking application. So this function here, benchmark, just takes a std function, just takes a function of our own definition as a parameter, and it takes a little label. And what it does is uses std Chrono to store a start time. And then we execute our function to be timed. And then we calculate the elapsed time, again, using our std Chrono facilities, right? And then we output that to our MCU debug stream. And so really what I've written here is Google benchmark, all in about 5 lines of code, right? And what we're going to time is my expensive function here. So this is just a kind of expensive function. It has sines and cosines and exponentials. And what we're going to do is use our std Chrono functions not only to do the timing of our function, but to kind of do an endless loop of delay and then evaluate this benchmark function. So benchmark in microseconds, my expensive function, and output true function. What we're going to do is go and compile and run this. Again, this is going to run on our dev board. And this is going to output our function. So again, we've kind of recreated a Google benchmark all in 5 lines of code using std Chrono. And all we had to do was write just a few lines of code. Our last little thing, we're going to implement a little bit of random and get some free beer, not beer, but library code. So the scenario is this. Your boss comes to you and says, hey, we're going to build a flameless candle. It's going to have an LED that has a variable intensity that has a really realistic candle function. In order to do that, you want to implement a random number generator with this probability density function instead of the usual uniform density function. So what that probability function really gives you is sort of a random walk that sort of moves with a small variation, and then every once in a while you get a big variation. And so this is going to effectively simulate our flicker activity of our flameless candle, and this is going to look really realistic and fantastic. And then before you say this is like a really contrived example, nobody would ever do this, just remember I work for a consumer products company, and we actually sold this product for a while, right? This is a flameless candle that uses sort of much the same statistical approach that I showed you in the slide. So fun with random numbers, right? So we're going to write our kind of bimodal or trimodal, depending on how you want to call it. We're going to write a distribution function, and we're going to make use of lots of functionality in the C++ standard library, right? It's including normal distribution for a first mode, normal distribution for a second mode, and we're going to use this uniform real distribution as basically a weighting function. So we're going to use that uniform function to kind of weight our probabilities between these 2 modes. And what does that look like? So our bimodal distribution has a operator parentheses, which takes a random generator device. It calculates a random number based on this uniform distribution. And then based on the value of that number, we either pick this first mode or we pick the second mode for our distribution. And so that just sort of sets the weighting of our 2 modes of our bimodal or trimodal. And we use the sinum function to make it symmetrical about the axis. So what we can do is we can go on the PC and we can, using totally available facilities on your PC, std random device, and then we instantiate our bimodal distribution, and then we can calculate a bunch of random values using this distribution, using our PC's random number facilities. What we could do is we can notice that our microcontroller, since it's capable of cryptography on the microcontroller, we actually find that our microcontroller has a random number source, a random data source. So what we can do is, again, in our namespace MCU, we can create a random device, configure that device, and then give it an operator parentheses that gives us random data. And so we can do the same thing with very minimal changes, create our random distribution like so, and wrap up with one last demo. Here, and I will show you the code really quickly. So we are creating our bimodal or trimodal distribution, however you want to see it. We'll create a histogram array, and down here we're basically going to create a ASCII art histogram array. And so what we're going to do is just build and run this application, flash it on the board, and here's our ASCII art numeric distribution. So this is actually generating random numbers in a very unusual distribution using the random number facilities in our microcontroller. So with that, I'm running a little short on time. I'll say thank you and encourage you. If you have questions, please put them in the Q&A. And the moderator is going to help me answer a few of them. And I'll make sure that if I don't catch you here, I'm going to make sure that your questions get answered in the Discord chat. So be sure to stop by. Be happy to chat there.